In this video, I want to take a look at the error bound for using a quadratic approximation. Where does the formula come from? So I'm going to shut myself off so we can see what we're doing here. So it starts the same as the last video. This is the equation we got in calculating the error bound for the linear approximation, right? We did an integral two different ways, and we had these two equations that equal each other. Now I'm going to go through these calculations pretty quickly because they're exactly the same as the last video, right? We write it like this. We integrate by parts here, and in integrating by parts, we go through all this stuff, and we end up generating the quadratic polynomial, quadratic approximation, plus this integral, which is going to be where the error comes from, that the difference between the function and this quadratic polynomial is whatever's right here. Okay, so we're going to try to get a handle on what is that term. So yes, here we go. Let's come all the way down to here. The error is the difference between the function and the quadratic approximation, and we've seen just above that that's equal to this integral. So the absolute value of the error is the absolute value of that integral. Moving the absolute values to the inside of the integral actually makes things bigger, because this might be a negative function. This is definitely a positive function, and hence you're integrating a bigger function. And yes, then the absolute value of a product is equal to the product of the absolute values, so that's an equal sign there. And now I'm going to try to get a handle on how big things really are. The third derivative of this function is what's sitting right here. So what I want to say is let m be any upper bound for the third derivative. Of course, as in previous cases, the smallest upper bound that you can choose is probably the best one to do. Give you the best idea of what the errors actually are involved. So any upper bound on the third derivative on this interval from b to x, right? The quadratic function has some bend to it, right? It has a non-zero second derivative, but it has a constant second derivative. And the function f might not have a constant second derivative. The second derivative might be changing. So that's being told to you by the third derivative. So the error in this is coming from the third derivative, because that's the difference between a general function and a quadratic, is that potentially changing second derivative, which shows up as a non-zero third derivative. Okay, so replacing that with m means we're replacing it with something bigger, because m is chosen to be an upper bound, so something bigger than that third derivative, which then allows us to do the integral. Because m is a constant, it can come out. What's left is just a polynomial. It's a quadratic, x minus t squared over 2. Remember, t is the variable here. So with the u substitution of x minus t, du is minus dt, and hence the minus sign comes out when you integrate. Anyway, the squared integrates to a cubed over 3. So there's already a 2 in the denominator. There's now a 3 there as well, and hence the 6. Okay, plugging in the x, plugging in the b. X goes plugged in for t, and b gets plugged in for t. The x minus x is 0, and then the minus minus becomes a plus, and we end up with this formula right down here, where the error in using the quadratic approximation is equal to an upper bound on the third derivative times x minus b cubed over 6.